Lecture 20, Advanced Concurrency Problems. Okay, so up till now we've covered the three sort of most famous, most well-known standard concurrency problems. We're quite familiar with them. We have a good understanding of those, and I think we don't have to worry about repeating all of the details of that. But we should consider a few more advanced scenarios. And these advanced scenarios are, not only are they not as common, but we're not going to go into quite as much detail about them. Part of that is, at this point, we have the toolkit already that we need to work with them effectively, to understand how they are supposed to work, and what is supposed to happen. And part of it is because they are less common, we'll probably not encounter them as frequently, so we don't have to worry quite so much about making sure that we have all the details down. On the other hand, these are still important and interesting questions, and hopefully provide a little bit to think about when it comes to addressing whatever needs of whatever system you are interested in analyzing or designing. And so today we're going to consider the pizza maker's problem, as I like to call it anyway, the barbershop problem, and then the chemistry problem. And we'll get into each of those as we go. These are by no means all of the possible concurrency problems that exist. In textbooks, in particular the Little Book of Semaphores, there's tons and tons of problems, and they are quite frequently well thought through and thoroughly addressed. So the first one is the, pizza maker's problem. Okay, so in the book it's called the cigarette smoker's problem, but smoking is bad for you. Pizza, well, not exactly health food, is amazing. Delicious, delicious pizza. So that's actually the one that we are going to focus on first, and we'll call it the pizza maker's problem. But if you see it elsewhere, it's called the cigarette smoker's problem. And the items that are needed are slightly different, but the idea is effectively the same. Okay, so our scenario, Iron Chef, our today's secret ingredient is Tide Pods. That joke was controversial. I wasn't sure if I was going to do it, but well, I hope you like it. Now, our new show is going to be one of those, Food Network cooking contest shows. There was a time Food Network actually aired, shows about cooking, but those have all moved to the Cooking Channel, and now the Food Network is all competition shows. So, hey, we have a competition show that we want to talk about. And our new show is going to be hosted by some famous TV chef personality, because definitely, being good in the kitchen means they are highly qualified to host a game show. That's how it should work. And we're going to write a simulation of this scenario. And the goal is for people to make pizza. Fine. And a pizza requires 3 ingredients: dough, sauce, and cheese, and you have to have all 3 ingredients for it to be a pizza, otherwise it doesn't meet our definition of pizza. If you have just dough and sauce, that is tomato flatbread. If you have dough and cheese, it's cheese breadsticks. If you have just sauce and cheese, it's low carb, but it's a mess. So, it doesn't meet the definition of pizza. A pizza has to have dough, sauce, and cheese. So in this sense, I suppose we are holding quite closely to what Italians would consider pizza. If you go to Italy, they think, the idea that you can put random toppings on a pizza to be rather strange, I think. Now, this could be a real TV food cooking contest show, because the rules are kind of wacky, and you would think to yourself, why does it work like this? So there are 3 contestants, and each contestant has an unlimited supply of any one ingredient. So contestant A has an unlimited amount of dough, contestant B has an unlimited supply of sauce, contestant C has an unlimited supply of cheese. Each contestant needs to get the other 2 ingredients that they do not have, and then make a pizza. They will try to make pizza in a loop until time is up, and accordingly, when they have those ingredients, they can make the pizza, put it in the oven, and get started on the next one once they have the ingredients that they need. So that describes contestant behavior. So if you're contestant A, you just need to get these other 2 ingredients, and you're ready to go. Now, at the start of the episode, the host places two different random ingredients out. So the two ingredients will always be different. So it could be sauce and cheese, it could be sauce and dough, it could be dough and cheese. They won't both be the same. There will be two of them, not three, but two. And so contestants can signal the host to ask for more ingredients, but they shouldn't do so unless they actually need something. So if you currently have what you need, then you focus on making pizza and you don't tell the host put out more ingredients. And every time the host is woken up, the host again places two different random ingredients out on the table. And when an ingredient is placed on the table, just to sort of give you some idea of how the communication happens, the host posts on the semaphore associated with that ingredient. Even at this stage, I think we are starting to get a picture on what does the layout of our solution look like. What are the semaphores that we are going to need? We've already kind of established that there's an associated semaphore with each kind of ingredient, so one for sauce, one for dough, one for cheese. And by the reference, it says every time the host is woken up or signaled, then that indicates there's some sort of host semaphore where the host is going to wait, and then when contestants need ingredients, they poke and say, hey, could you put some more things out on the table? So, okay. Our scenario maybe seems a little bit contrived because I'm talking about a cooking competition show in which there are the following characters and the following rules, and it would be reasonable to ask, well, does this map to any kind of real-world scenario? It is my hope I can convince you the answer to that is yes. We have a scenario where there are resources being provided by some external system. The contestants in this case are processes that want certain resources. And the thing about it is that not every system is so kind as to allow you to request exactly what you want. Sometimes you just get what is available, and therefore there's a little bit of figuring out, is this something that I want? Is this something that I need? On that same token, we shouldn't be wasteful. Resources should only be requested when processes need them, and processes shouldn't be hoarders, stockpiling resources that they do not need, because that potentially deprives other processes of getting those things that they would otherwise want. So, we want to use resources efficiently, try to be effective in how we use them, and it means that processes should only take what they need. They should only take a resource when they can do something useful with it. And for our scenario for the pizza makers, it means if you have an unlimited supply of dough, you shouldn't take dough because you already have more than you could ever need, because this is something that other contestants could be using. On the other hand, if you have sauce already, even if you don't have an unlimited supply of sauce, you shouldn't take much more sauce than you need, because again, you are depriving potentially a different contestant of that resource, which they could actually do something useful with. So, okay, with a sort of baseline understanding of this program, we could think about how we would go about making it in an implementation. And you have to make some decisions, and our decisions could make the problem either trivial or impossible. Yeah, so how hard do you want this to be? I mean, we want to choose a reasonable difficulty, but let me motivate a little bit our choices for this problem. So in the impossible version, you can't modify what the host does. That's okay. That one on its own isn't bad. That's actually fairly reasonable because you don't necessarily control the other system. Like if you have a client and the other side is a server, you can't just arbitrarily make the server do things if it's not something that you offer. I've recently encountered a thing where there's a button in the UI to download a PDF, and there's no API endpoint for this, and I can't make them add it on the other company. I can't make them add it. All I can do is ask, would they consider adding it? And they will probably tell me, no, or maybe in the year 2525. Sure, I can wait. No, I can't. But modifying the host's behavior, being disallowed is at least somewhat reasonable, because you can agree, I think, that you can't always control the remote system. On the other hand, in the impossible version of the program, you're not allowed to use conditional statements, so like no if statements in your program, which is kind of, well, silly. Like, what kind of programming language doesn't give you if statements? So, and like artificially handicapping your solution by saying, well, I guess you can't use this very basic, super important construct that you learned in introductory programming. Good luck. Sure. Yeah. That's definitely the thing. Now, maybe in a cooking contest show, you could get away with that as some sort of sabotage on a show where contestants are allowed to sabotage one another. But it's not that kind of show. It's not that competitive. In the trivial version, the host just tells the contestants whose turn it is. So the host is going to put out sauce and cheese, and it says, aha, I know exactly which contestant this is. So sauce and cheese corresponds to contestant A. So I'm going to call contestant A over and say, hey, you should do this thing. The negative part about that is that it requires the host system to know too much about the contestants. It has to know in advance exactly what everybody wants, and then decide accordingly how to allocate resources. That's kind of not realistic either. If you are making an API and you expect people to call this API, you can tell them what possible things it returns, but you can't predict every use of that API, and getting it is unnecessary or unnecessarily difficult. And furthermore, it's not your problem. If people want to consume the API for some purpose, let them figure out how to do it. Why should it be your problem? So the interesting version is just the restriction that you can't control the host behavior. So that one I can live with, and it works even in our analogy here with Pizza Maker's Problem, because TV chef personalities are wacky individuals, and they do wacky things. I mean, you don't think Guy Fieri would take instructions real well, do you? I mean, look at that shirt he's wearing. If nobody has convinced him that that's a bad idea, I don't know what else you could get him to do or not do. Also, if you are ever interested in the very best restaurant review ever, you should look up the New York Times review of Guy Fieri's restaurant in Times Square. You should. It is incredibly entertaining. In any case, so we'll imagine that our TV chef personality, just does wacky things, and you can't make them not do wacky things because, just look at him. Okay, so let's imagine then that we want to make some pizza, and this is our first draft of our solution. All semaphores start at 0 except for the host, which starts as 1, so the host will run the first time. I don't want the host to get blocked immediately when the host is going to start. But let's get started. Contestant A waits for sauce. When sauce is signaled, get sauce. When cheese is available, get cheese. Make pizza, and then tell the host, let's go. Next. Okay, and it's analogous for contestant B and contestant C. Wait for dough and wait for cheese for contestant B, and then wait for sauce and then wait for dough on contestant C. And so, let's take a look and ask ourselves if this works. Now, it requires us to take a little bit of a look at what the host does, and I didn't put any pseudocode for the host, but given our understanding of what the host does, we should be able to imagine fairly easily what his behavior is. That if the host is going to be activated, so we'll have a wait on host. If the host is unblocked at that point, the host continues. Choose a random ingredient and put it on the table, and then post on that ingredient, and then choose a second random ingredient, put it on the table, and then post on that ingredient. Again, the second random ingredient will not be the same as the first, and that's it for the host. And I'll go back around the loop and wait for the next time that they're woken up. So when the host starts, wake up and put 2 random ingredients on the table, and then go. Okay. So, let's take a look at this, and does it work? All right, well, we should consider our usual sort of mechanisms of making sure that things work as they should. There's a lot more wait statements shown here than there are post statements, but if you use your mental model of the host, then things kind of check out. If the contestant A waits on sauce and cheese, okay, there's decrements on each of those, but the host will post on sauce and cheese, for example, as one of the possible things when he wakes up. So that part's okay. Similarly, post on host will be matched by the host's behavior of wait on host, so that, again, shouldn't be a big deal. Lock ordering. Also something to consider. A waits on sauce and then cheese, B waits on dough then cheese, and C waits on sauce then dough. Now, if we sort of map that out, do we always wait on these things in a reasonably consistent order? Right? It seems that first sauce, then dough, then cheese is implied as an order, and that seems to be sort of held to consistently. Right? We can agree on that. Okay, so what's our conclusion? Well, I mean, our conclusion should be that deadlock can easily occur in this scenario. Suppose the host puts out sauce and dough. If contestant B takes the dough and A takes the sauce, both of them are blocked and nobody gets pizza, right? So sauce and dough are put out, contestant B takes the dough and waits for cheese, and sauce gets taken by contestant A. And then everybody is stuck. Contestant C is still waiting because when the host posted on sauce, it could have woken up either A or C. It turns out it was A, and that didn't turn out great. You could actually still get the same behavior even if contestant C was woken up. Contestant C waits on sauce and gets it, but contestant B got to the dough first, and then C has the sauce but not the dough, B has the dough but not the cheese, A still has nothing, and we end up stuck. There's other possibilities for how you get stuck. It's just a question of what ingredients you put out. Sometimes if you sort of choose the wrong ingredients to put out, everything works out fine. Actually, if the host puts out dough and cheese, then contestant B will actually make a pizza and succeed. So there is a wrong answer in terms of what ingredients you put out there. That could lead to a deadlock. You can't just say, whatever ingredients the host puts out, it could happen that one party gets one of them and one gets the other, because that would actually be wrong. If dough and cheese are put out, the only one who's waiting for dough at the moment is contestant B. Contestant B will get it, and then at that point, cheese is out, but the only one who's waiting for cheese at this point is contestant B, so contestant B will get it, make a pizza, and then post. So deadlock did not occur there, because contestant B successfully made a pizza, and we made it through a round of this game show. However, the sauce and dough option definitely causes the deadlock, so yeah, that's something else to watch out for. What about if you put out sauce and cheese? Does that cause a deadlock? The answer is to that also yes, but it's even a little bit stranger. So if you put out sauce and cheese, it's possible contestant A gets both and they finish and leave, fine. But it's possible that contestant C gets the sauce and then is waiting for dough. Dough has not been put out. Contestant B can't start because dough is something that it's waiting for, and contestant A is still waiting for sauce and it doesn't get it. So in this case, we have a deadlock where cheese is on the table, but nobody's interested in it right now. And yet all three are stuck. So there's lots of different ways that you could get stuck, but you can't just say, yeah, any scenario causes a deadlock. You actually do have to be specific. Okay. So part of the problem that we have is that a contestant doesn't have a good way to assess what the ingredients are before they try to get them. And once it's there, if it finds the ingredients match someone else's needs, we don't call that contestant over. If you are contestant C and you get up to the table and you see, oh, what I have here is actually a better match for contestant A, you don't say, oh, actually I'm going to skip this turn and let contestant A have these things. That would be clever, but to make that work, we would need a way to check what ingredients are there, and semaphores kind of don't let us do that. Can we work with what we have? Is there a good way to make this happen? If we think back on our toolkit, maybe we have something that would help us to get this done. So you might have said, what about try-lock behavior? Try-lock behavior might actually be a solution to this, as long as you can live with the fact that this might be a bit of sort of busy waiting. So in try-lock behavior, a contestant will go up to the table and try to acquire ingredients. If they don't get the 2 ingredients that they want, they put down the ones that they did get. So try to get dough, try to get sauce, but there was sauce and cheese. So I got one of the things, I'm going to put down the one thing, and then I'll go back and try again. If resources can be produced pretty much immediately, and so you just take what you need and leave, and you might have to retry a couple of times, but no more than that, maybe you would consider this kind of solution acceptable. That might work. However, it is a little bit effort intensive for the contestants, and they might spend a lot of time sort of fighting with each other about ingredients, and picking ones up that they don't need and then trying to put them down again, and that's not always ideal either. So maybe we aren't super thrilled with that as a solution, and we would like something to be blocking. That is, that we would like to we'd like to wait until that is the case. You could actually improve on this, incidentally, by having a semaphore where every contestant waits, and the host just signals n times and says, "All right, all contestants, come up and take your shot, see how you do." That's not ideal, though, because there is a possibility that the same one gets woken up 2 times because they go up there quickly, they check it, they leave, they go back. There's also a requirement for the host to know exactly how many contestants there are. In our example scenario, that's allowed, but in real life, that might not actually be the case. So, what can we do about this? Well, the answer is we can hire a helper. Holy pizza, Batman. Why does Batman wear dark clothing? Batman doesn't want to get shot. Why does Robin wear brightly colored clothing? Batman doesn't want to get shot. So now every contestant has a sidekick, Holy Pizza Batman, and they get a helper. And the job of every helper is to more or less help the contestant to make pizza by figuring out whose turn it is. Okay, so effectively what would happen in this case is that helpers will effectively try to tell the contestants if it's their turn based on what they know about the system. So that's actually fairly complicated, but we'll explain a bit of the setup. So there are Boolean variables dough present, sauce present, and cheese present, and they're all initialized to false. We will protect them with a mutex or a semaphore called mutex. And helpers update these variables, and based on the known state of the system, they tell the contestant whose turn it is to come up and get ingredients. So, okay. We've made the problem a little bit more complicated in that there's now different actors that are involved in the system, and it's not just the host and the contestants, but this is manageable. We're not asking too much for every contestant to have a little sidekick. So every contestant now has a semaphore, we'll call it for contestant A, which helpers will post on when it's telling contestant A that it is your turn. Contestants are still responsible for telling the host to put out more ingredients, but the code of the helpers, they're all analogous, so if I explain one, presumably it sort of explains them all. But helper 1 is the person whose job it is to check if there is sauce, helper 2 checks if there is dough, and helper 3 if there is cheese. So when sauce is put out on the table, helper 1 is activated. And if that's being the case, then helper 1 waits on the mutex, the one that's used to control access to the shared Boolean variables. And when allowed to proceed, if dough is present, then the helper marks dough as being not present and tells contestant C it's your turn because sauce and dough are presently available, and says, yep, contestant C, you're on. If there's no dough, but there is cheese, then we mark the cheese as being not available, and we tell contestant A, all right, you're up. And if neither dough nor cheese is there at the time when helper 1 is looking, then it just marks sauce as being present, and then leaves. It's the end of helper 1's turn. And the same is true for dough. When dough is put out on the table, helper 2 is activated. If there is already sauce, tell contestant C, here you go. If there's cheese instead, tell contestant B, let's do this. Otherwise, just mark dough as being present and go on. And again, it's totally analogous for helper 3, where helper 3 waits for cheese. And so if you are the first helper activated, you get there, the first ingredient is been placed out on the table. You just can't do anything with that because you don't know what decision to make until you know what the second ingredient is. In that case, you just mark down the state as being that the sauce is present if you are helper 1, the dough if you are helper 2, the cheese if you are helper 3, and that allows whichever is the second of the helpers to actually get there and make that decision. So whether it was dough or cheese, it will activate either helper 2 or helper 3, and that person will then decide, okay, here's what I see as the state of ingredients, and then actually activate the correct contestant. And so, yeah, our analysis of the helper is wake up when your ingredient is there, lock the mutex, manipulate shared variables, make a decision about what to do, and then tell the correct contestant, hey, it's your turn. So in this case, it's always better to be the contestant than the sidekick. The poor sidekick has to do all the work, and the contestant takes all the credit. So, that's not a great position to be in. Contestant code is very straightforward. If you're a contestant, you wait until you're called, you go up, you get what you need, you make a pizza, and then when the pizza's in the oven, you can signal to the host saying, yeah, we can put out some more ingredients, and that is what the host will do. So, contestant B, same thing. Wait until they're signaled, get their ingredients, wait for contestant C on its semaphore, and then that contestant will get what it needs, and, there really isn't very much to add that. So, this problem, you might say, well, it seems a little bit strange. Right? Like if I'm a host and I put out 2 random ingredients only when I'm signaled or whatever, that's probably kind of frustrating for people who want to use this service, right? Like I'm offering some service, and when people call and they say, hey, I need some things, then I just put random things on the table. It would be better, of course, if people could ask for what they need, and then, the host would give them what they need. It wouldn't be, that great of a contest show at that point, because, any TV contest show has to have at least one ridiculous rule that makes no sense, because otherwise, it would not be exciting. But maybe you could make an argument, and I would even probably buy your argument, that this situation isn't super realistic, that we're faced with something that isn't so plausible. I mean, maybe, but maybe not. Okay, so maybe a general version of the problem makes it a little bit better. And that is the general version of the problem changes the rules about what the host does. In the general version, the host puts out ingredients periodically without being signaled to ask for more. So now the host just every so often puts ingredients on the table as they become available. Now this is much easier to argue is like a relevant scenario for the kind of thing that we are used to. That if the thing being put on the table is some resource, and resources become available as soon as those resources are generated, well, they're generated at some rate, and they become available at that rate, and not every resource is exactly what you need, but you can check and see, is what I'm looking for there? If not, I'll try again later, and otherwise, someone else can have a turn. So, yeah, I think this increases the plausibility of this particular scenario. I mean, you may still disagree, and that's okay. But I at least think that it's easier to motivate that this could actually happen in a real system, and not just as a contrived, like, hey, imagine this weird world in which no sensible rules are enforced. Okay, so how do we modify our solution to deal with that? Well, there's no longer a need for contestants to say that they want more resources. So if I go back to the contestant code, then of course the last statement here under each of the contestants can be deleted because those are no longer required. But what about the helpers? So the helpers in this case, if we recall, have like wait for whatever ingredient, then lock the mutex, then make a decision based on what they see, and then post on the mutex. And the idea is really not too different. The idea is still going to follow that same general framework where helpers go up, look at the state of the world, and make a decision about what to do. However, we have to include in our thinking the possibility that there might be more than one of an individual ingredient. And why is that the case? Well, it's just a question of time. If the host puts out ingredients very close together, well, the host might have put out sauce 2 times before somebody got there to direct a contestant to pick it up. So, yeah, we now have to consider that possibility. All right, so what would we change? This is another one of those, so I'll give you a minute to think about it, and then we'll go on. Okay, this one is, again, reasonably straightforward, that if now we can have multiple instances of a given ingredient, then it means we should keep track with the counter as opposed to just a Boolean, whether it's present or not present, which would tell us how many are there. Because if there's 3 portions of sauce or 2 portions of dough or 1 portion of cheese, that's all interesting information, and we need that. So let's see what the helpers do now. So instead of Boolean variables, we have an integer counter, and I've just named them for the sake of this num dough, num sauce, and num cheese, and they'll all be initialized to 0. And if we put this all together, we end up with the following code, pseudocode. So helper 1 waits for sauce, wait on the mutex. If the number of dough is greater than 0, then number of dough is decremented. Unfortunately, as I look at this, the way the typesetting has set up the minus minus, they overlap. And if I zoomed in on the affected line here, so like number dough minus minus, the 2 minus symbols overlap a little bit, so there isn't obviously a space in between them. But that very long dash should be read as minus minus. I can see that in the notes it is correct. And so if the number of dough is greater than 0 and sauce has been placed on the table, decrement the count of dough, post on contestant C, telling contestant C it's your turn. If the number of cheese instead is greater than 0, decrement number of cheese and post on contestant A. Otherwise, just increment the number of sauce. And as before, helper 2 and helper 3 are analogous. Just swap the names. Wait for dough if you're helper 2. Wait for cheese if you're 3. And then the decision that you make as helper 2 is based on, well, if there is dough and there is sauce, tell contestant C. If there's cheese as well as dough, tell contestant B. If there is cheese put out, then contestant B will be signaled if also there's dough, and contestant A will be signaled if also there's sauce. And there we have it. So this pattern, this sort of way of addressing a problem is referred to as a scoreboard. That is to say, there is a set of variables, in this case they're the integer counters, that are used to keep track of the current state of the system, and those variables are viewable from every thread. As threads go about their actions, they take a look at the current state, the scoreboard, and they decide how to act based on that. Why a scoreboard? Well, if you are like in a stadium and you are watching a sporting event, then you will see there is a scoreboard. The scoreboard is usually positioned such that it's visible from almost everywhere within the stadium. And then, of course, everybody can know what the score is at any time. And that's why there is the scoreboard name for this, that there is somewhere a very visible state, and the state can be looked at by any thread, as long as it's done with appropriate mutex corrections, and they make their decisions about what to do with the knowledge in mind of the score. So the scoreboard pattern will apply to more than just the pizza making problem, with or without sidekicks. But it is a good. This problem is a good introduction to why that is an interesting problem and why it is useful, and maybe you can think of other problems, not specifically related to making pizza or similar, where a scoreboard situation actually would be helpful, and it's anywhere that threads have to make decisions about what to do based on the current state. Okay, our next advanced concurrency problem is Rabbit of Seville. No wait, Barber of Seville. This, I suppose, is the second most famous opera ever after Die Walküre, because that was also a Bugs Bunny killed a wabbit, if you are a fan. So, what about this? Well, it's actually called the Barbershop Problem. So the barbershop problem is another one of those things that was originally proposed by Dijkstra, and I'll assume that you are broadly familiar with the concept of a barbershop, but just to make it clear so there's no possibility of confusion, a barbershop is a place where customers get their hair cut, assuming barbershops are open, and a barbershop consists of a waiting area, and a waiting area has N chairs, and there's also a chair for the barber. The barber doesn't actually sit in the barber chair, but it is the chair you sit in when the barber is cutting your hair. Okay. Now, a barber behaves according to the following rules. If there's no customers to be served, the barber goes to sleep. That is to say, the barber doesn't busy wait. The barber just will sleep while waiting for a customer or more customers to arrive. If a customer enters the barber shop and all of the chairs are occupied, then that customer leaves the shop. So that's the barber is currently cutting somebody's hair and all of the waiting chairs are full. Then the customer just leaves the shop. Why? Because the lineup is too long, they're not going to wait. If the barber is busy, but there are chairs available in the waiting area, then the customer just sits in one of the free chairs and waits their turn. And if the barber is asleep, the customer wakes up the barber. That is to say, if they are like the first customer to enter and there's no customers currently in there, the customer wakes up the barber. Okay, so you could imagine this is a reasonable sort of model of a barbershop. Is this a reasonable model for anything sort of in the computer? Well, yeah. We'll come back to that towards the end of our discussion of the barbershop problem. But I hope you will take my word for it now that yes, this is actually a plausible scenario. So, if I wanted you to implement this, I would give you the following information. I would say customer threads should call the function getHairCut when it is their turn. If the shop is full, that is, the barber is currently busy and all the chairs are filled, then customers should use the return statement, that is, they just give up and leave. And the barber thread will call cut hair, again, when a customer is waiting and is ready. And the barber can only cut one person's hair at a time, so obviously only one thread should be calling get hair cut concurrently. And for the purposes of just writing down our pseudocode in a bit of a simpler way, we'll say there are external forces that cause customers to appear and for the barber to keep working, so we don't have to write a loop for either of them that says while true, continue, anything like that. Just the content of the loop that we might otherwise normally write. So okay, let's take a look at our plan. we're going to need to keep track of the number of people who are in the waiting area somehow. So we'll have an integer counter for customers, which is called customers, unsurprisingly, and it should start at 0. We will obviously need a mutex for this called mutex, and it equally obviously starts as 1. And again, each customer wants to update this counter, so its shared data has to be protected by mutex, straightforward. And we'll have 2 semaphores, customer and barber, that are going to be used for the customer and barber to communicate with one another. Okay, so let's write down sort of a brief outline of this code. Okay, we have a customer on the left, the barber on the right. The barber code is much simpler, so I'm just going to start there. There isn't a lot to think about. Wait for the customer, so the barber waits until someone indicates that they're here. That would wake up the barber. The barber will signal. Again, you could use post for this. As before, in most places I've replaced signal with post, but you should be able to consider both of them equivalent, so it's not weird if you see it. So wait for customer, signal barber, cut hair. Okay, so what is up with signal barber? I mean, we're the barber. Why are we signaling on that? This is something that I was referring to somewhat earlier when I said, well, you see, sometimes the order in which things happen, or the names that we assign to things, make more sense from one perspective than the other. So, like the barber is going to wait for a customer. That makes sense. Okay. But the barber is going to signal barber. That doesn't make as much sense, but it makes more sense when you think of it from the perspective of the customer, because what the customer wants to do is wait for the barber. So think of it as the barber signals that they're ready, and that calls forward the customer, and then the barber cuts hair of the customer. Very good. Okay, so as for the customer, wait on the mutex, check to see if customers is n+1, that's our give up condition. And so n+1, that means all the n waiting chairs are filled, plus the one in the chair who's actually getting their haircut right now. And you'll notice that we do not forget to signal mutex here in this if block, which is to ensure that we don't exit from this function while still holding onto the mutex. That would be bad. Otherwise, increment the number of customers and then signal on the mutex. We will then signal on customer. We will then wait for the barber. Once we have gotten our turn, so we've been called forward by the barber signaling on that semaphore, then we get our haircut. We can wait on the mutex. We can then decrement customers, and then we can signal, and we're done. Again, on this line with customers, the font unfortunately has stretched out the dashes a little bit, so this again should be customers minus minus, and not customers very large dash. Okay, so yeah, if our customer shows up, and the waiting area is full, they leave. If we forgot to do that, they would sort of no longer be able to enter. Otherwise, we just keep going, and we wait our turn, and we eventually get called forward. Keeping in mind that there is no strong requirement that when we wait on the barber semaphore that we get woken up in first come, first served order. That clashes a little bit with our expectation about like how a barbershop would actually work. You would expect that it is first come, first serve if you have a walk-in appointment. Otherwise, you might get pretty mad. But we'll live with that for now. You might imagine that it's a fancy barbershop where there are member classes and executive members get to go for. I have no idea. I wouldn't patronize such a barbershop, I suppose, unless I was an executive member. But okay, digression aside about fairness and the proletariat alike. Let's take a look at this code. Is there a risk of deadlock? Is there a risk of starvation? So we'll start with deadlock, and you tell me what you think, and think of what you think, and then I'll give a bit of a discussion of it. Okay, so one of the things we should observe is there isn't the nested wait pattern that we're used to. That's a good sign, but like not enough for us to say, well, I'm sure this could never happen. So, I mean, let's take a look. If the barber gets blocked, it's because the barber is blocked on waiting for a customer. And the question is, will a customer always get to the signal customer statement? And I mean, we can see that the answer to that is usually yes. If a customer comes in and leaves, it's because the barbershop is full, and that means, of course, that there are customers ahead in line, and those customers ahead in line have already called signal on customer. And that means that the customer semaphore can't have a negative value or something while the barber is waiting, and there are customers leaving and saying, well, I guess I give up. There have to be customers for any incoming new customer to leave, and therefore the value of the customer semaphore will have to be positive, so the barber won't get blocked on that. If there are no customers, then it only makes sense for the barber to get blocked, and this barber will eventually get unblocked when the first customer arrives, so waits on the mutex and skips over the if block and then signals on customer. What about customers? Do they get blocked anywhere? Well, they can get blocked waiting for the barber. But if they're waiting for the barber, the barber will signal on customer eventually and cut hair. And I've said there is, some external force that makes them run in a loop, and therefore I don't think we're that worried because there's nothing that could hold up the barber. You'll notice, though, that if you accidentally swapped the order of wait, barber, and signal customer in the customer code, then you could actually have a deadlock because you would have a customer that would wait for the barber to signal, and the barber would be waiting for the customer to signal, and that very much looks like some of the examples that we saw very much at the beginning of our concurrency discussion, where if we do signaling in the wrong order, then we end up with this problem. So, okay, no real cause for deadlock concerns. What about starvation? What's starvation? Well, okay, right off the cuff, we can say for sure the barber won't starve, because if there are customers, the barber will activate and the barber will cut their hair. No worries. We probably weren't that worried about the barber starving. But what about customers? Well, there's two kinds of customers. There's customers who successfully get in line and those who don't. So the ones who do get in line, so they get past the if customers is n+1, then they signal on customer, they wait on the barber, they will eventually get a turn. At some point or another, they will get called forward. In fact, they will wait some amount of time, but it's a finite period, particularly because the size of the waiting area is limited, and we can expect that customers don't get delayed indefinitely, but it could be quite a while. But what about customers who just give up in frustration? The ones who do look at this and say, the room is full and I'm leaving. They want to speak to a manager. It is, in fact, the official "Can I speak to a manager" haircut. So we can maybe say that customers who give up in frustration are disappointed, but you might actually make an argument that this is better than the alternative. Now, is this better than making them wait forever? If a customer is waiting a very long time, they're pretty upset. If they're told they won't get service today, they can go to a different barbershop. They can come back another day, come back some other time. That's why there's a limit on the waiting area. In a real life scenario, a barber is only human and can only cut so many people's hair in a day. The exact number, of course, depends on how long each haircut takes, which depends on the person and what haircut they want. But there's a limit of some sort. At some point, the barber will go home for the day. And also, so many people can fit in the waiting room. If there's too many, nobody can move around, and it violates fire code and is dangerously unsafe. But actually, I think this is a very good lesson for services in general. And that is that services have a capacity. When things are overloaded, it's better to tell clients that, listen, the service is overloaded right now, please wait and try again later. Clients can choose what to do. And it's either like wait a while and try again or go to a different service. I mean, if it's Quest or something, like, there's no alternative to Quest, so you can't just, use some other system. But you could decide, I'm going to wait a while and try again, and that's okay. If the game that you want to play, requires a server for multiplayer and all the servers are busy, you can play a different game. You wanted to play whatever popular shooter is currently popular, keeping it topical, then, and all the servers are busy for some reason because, some new giant content patch just came out. It's like, well, we can, like, stare at the loading screen, or we can, just do something else, play a different game, go outside, do anything you like. And that's actually helpful, because if you don't tell customers or clients or callers who invoke the service that this service is not available right now, or it's overloaded, or something like that, either they wait an unreasonably long time and they're more mad, or you just keep piling so many people in that the service crashes, or at least is degraded for other people who are actually playing. And so, given a choice between making some people happy and some people unhappy, and the alternative of making everyone unhappy, you probably agree that the choice where only some people are unhappy is better. So, for that reason, thinking about capacity planning is actually a good idea, or at least recognizing that there is a limit and having a strategy for what to do when you are near to or at that limit. So, does the barbershop problem sort of represent any real-life scenario? Sure. I think, anyway, that it represents lots of scenarios where you have a service of some sort, and you have clients who want to get that service, and the service could be anything. The service could be, checking people's ID to verify that, this is actually an authentic document. So, you put in your driver's license information that you've been provided, and you can check it, and it will tell you pass or fail. That's a service. It is something you invoke, and it does a thing that you asked it to do, and it gives you a response. And based on that response, you can say, well, yes, I accept this as proof of identity in my banking, online banking system. Fine. That will work. But this service potentially has limited capacity. You can only make so many requests, and if the service is busy or overloaded, you need to know, well, I can't use this service right now, I need to try again later. If you don't do this, you can just sort of make your customers mad because the service is down, or alternatively, if you don't tell them it's busy, try again later, they just retry when it fails, and they do so in kind of a tight loop, and ultimately it overloads the service even more. So that's also bad behavior. You could replace verifying the driver's license identity checks with anything, really, in that situation, as long as you have a server that provides a service and clients who want to consume that service in some way. All right. That ends a little bit of our digression on the subject of services in general, and why the barbershop problem is a good mechanism for sort of reasoning about a lot of online services. The last problem that we want to talk about is based, of course, in science, and that is we want to do a little chemistry. So, chemistry cat, two men walk into a bar, one orders H2O, the second says, I'll have some H2O2, the second man died. If you remember high school chemistry, you know why this is bad. But before we do that, well, for right now, we need to escape the ice planet of Hoth. For those paying super careful attention, you will probably have noticed that the slides out of number at the bottom right has jumped rather suddenly, and that would be because I realized I was working with an older version of this, so I needed to bring in this. Based on some past experience in talking with some students, the H2O problem is quite complicated, and we need a stepping stone between where we are and where we're going to make sure that everyone gets the key idea, and we can build on the key idea to the more complicated H2O version, and that's an easier transition than just be, well, here's the H2O stuff, enjoy, good luck, easy, right? Slam dunk. Okay. So, those of you familiar with this film, truly one of the best ever made, will recall that the Rebel Alliance is trying desperately to escape the ice planet Hoth before Darth Vader can put an end to the rebellion once and for all. The Rebels want to evacuate the base with transports. Transports are escorted by a pair of X-Wing fighters. Now, transports have no hope of surviving if they are not escorted. The Star Destroyers will just knock them out of the sky. So fighters have to stay with their assigned transport. Now, under normal circumstances, Central Command would tell the fighters and transports what to do and when to launch, but that option is not available due to the ongoing ground assault, which is taking up all of Central Command's attention. For this reason, transports and fighters must organize themselves to make sure that they get out. Now, only one group of fighters and transports can launch at a time, because there's only so much covering fire the ion cannon can provide. And in this problem, we're going to treat a pair of fighters as a single unit, so we are really talking about two kinds of thread. We have transports and we have fighters. Okay. So, generally speaking, we can draw a couple of conclusions about how things are supposed to work. One is that since they have to go together, if a transport is ready but the fighters are not, the transport has to wait. Conversely, if the fighters are ready but the transport is not, then, well, fighters have to wait for the next transport. It's not too simple, but also not too complicated. When the fighters and transport are ready, they both use their respective launch functions, and they can leave, take off, fly out of the atmosphere. The transport is the slower one to launch, so we'll say the next group should not proceed until the transport finishes the launch process. We'll assume for the purpose of this that there are enough fighters and transports so that nobody is left behind, and the setup and creation of all of those is, again, something we will imagine is handled externally. We can just focus on the behavior of each kind of thread, although we do need to consider carefully what our initial values for our semaphores, etc. are. Okay, what do we need? Well, we need an integer counter for the number of fighters currently ready, called fighters, and an integer counter for the number of transports, and we're going to use three semaphores: mutex, fighter queue, and transport queue. So the names give away quite a lot about what these are supposed to do. I mean, the integer counters, I told you, but for the semaphores and mutex, well, we're probably going to use that to protect shared variables, notably the fighters and transports ones that I have just named. And fighter queue and transport queue look to me like places where fighters and transports line up and wait for their opportunity to launch. Now, one of the things, again, although it's called a queue, again, remind you for the 8 billionth time that a semaphore does not necessarily have first-come, first-served behavior for waking up threads that are waiting. But in this situation, it doesn't matter. All that matters is that fighters escort a transport. Which fighters are escorting which transport is not especially important. They can pair up however, and they will still escape. Hopefully for them. Okay, so initial values. Mutex is 1, fighter Q 0, transport Q is 0. We'll start with the fighters code and then over to the transport code. So fighters, wait on the mutex, and if transports is greater than 0, so there is at least one transport waiting, decrement the number of transports, and then post on the transport queue, thus telling the whatever transport is at the head of the queue, let's go, we'll leave, and then skip over the rest and launch. For fighters, however, if there's no transports ready right now, just increment the count of fighter escorts available, post on the mutex, and wait on the fighter queue, so wait for a transport to say, hey guys, let's go. And eventually, a set of fighters will be woken up, and they will then proceed onto the launch. Okay, you might be looking at that, even before we go on to the transport thing, and you say, well, so the fighter waits on mutex, and in the else block posts on mutex, but there's no post on mutex if we don't go into the else block. That is, if transports are ready, that doesn't happen. Doesn't that look bad? Doesn't that look wrong? Well, I mean, it looks wrong. It doesn't seem quite like anything else we're used to. But it's okay. You'll see that when we go through the transport code. But transport does post on mutex unconditionally. So the important thing is that as long as somebody does it, we're okay. The number of wait and post calls will be balanced when we consider fighters and transport in totality, but the work doesn't have to be divided evenly. So it can be the case that transport does more of the work here by calling post mutex on behalf of fighters, even though fighters might otherwise have normally done that. And if we look at the transport code, okay, wait on the mutex. If fighters is greater than 0, decrement count of fighters, signal on fighters queue, and then just skip over the else block, launch, and then post on mutex when we're done. If fighters are not ready, increment transports, post on mutex, and get into the transport queue. Okay, so there is, of course, some possibility that we don't feel comfortable with the unconditional post on mutex. The thing to remember is that mutex is really being used for two jobs in this instance. It's, number one, used to prevent concurrent modification of the transports and fighters counters. Makes sense. But it also prevents any second group from calling launch simultaneously with the first group. Because if fighters arrive and they have to wait, okay, they release the mutex, they wait, a transport arrives, and when that happens, it tells fighters, let's go, it launches, the fighters launch, and then after the transport has launched, transport posts on mutex, and until that happens, nobody else can launch. So, yeah, that second job is why we have this, is why we have the post mutex after that, and it just makes things a little simpler. We need fewer concurrency structures. There's less we have to manage. Are we maybe abusing the semaphore a little bit by using it for two jobs? I guess you could make that argument, but I prefer to think of this as fairly clever. It works the other way as well. If a transport gets there first and fighters are not ready, release the mutex, wait on the transport queue. When the fighters arrive, they note that transports is greater than 0, decrement the count, post on transport queue, wakes up the transport, and fighters launch, the transport launches, and the transport posts on mutex. So in the first workflow that I went through, where it was the transport that got there, and as the second one, well, it locked the mutex and waited on mutex, and then it posted on mutex at the end, so it does its own dirty work. In the workflow where the fighters get there second, then actually it does wait on mutex, but that's balanced by the post on mutex of the transport. So the transport does the work on behalf of the fighters. There's nothing wrong with it. There's no reason why that cannot be the case. It's a little unusual compared to what we have done thus far, but our wait and post statements, we'll see, are in balance. Every execution gets us eventually to a post statement after we've done a wait. So, I mean, is there a risk of a deadlock? Let's look it over. Okay. One thing that's noteworthy is there's no nested waits. In fact, we really go out of our way to prevent that, because in both cases where fighters and transport are going to wait on a queue, they make sure to post on the mutex first. So there's nothing there. They won't be blocked as a result of that. The only way for fighters realistically to get blocked is that, well, there's no transports ready, and some will soon arrive. The only way transports get blocked is if there are no fighters ready, and again, they will be ready soon. Both fighters and transports might have to wait if another group is launching at the moment, but that's okay. If they're already at the launch phase, that will resolve when the transport finishes launch and posts on mutex. What about starvation? Any risk of that? Well, not really either. As long as there are matching numbers of fighters and transports, they will eventually meet up and get to launch. Potentially, under the constraints of the problem, if there are way more transports than there are fighters, then transports can't launch because we've run out of fighters. But I said, in the assumptions about this problem, that that's not a thing. So there will be sufficient of each so that nobody gets left behind. And as long as that assumption is true, then we will be okay. Everyone will meet up with one another, and they will eventually launch. So, in the words of Captain Nita, good. Our first catch of the day. All right, now on to the science. I think we got over the hurdle of the new thing being sometimes somebody else does our job for us, and we'll see the more complicated variant of this, which is the H2O problem. So now there's two kinds of threads. Oxygen and hydrogen. The thing that is different about this as compared to the Rebel Alliance trying to escape from Lord Vader is that basic chemistry says water requires 2 hydrogen and 1 oxygen, and this time we're going to treat hydrogen as being independent from one another. So they don't travel in a group, they don't travel as H2, they just travel as individual hydrogen molecules. So to assemble the desired molecule, water, a group rendezvous pattern is needed, but it's not just one of each. It's now we need 2 of hydrogen and 1 of oxygen. And so when each thread passes the barrier, it should call the function bond, which creates water, and the solution should function such that all the threads from one molecule invoke bond before any threads from the next molecule. So, as before, we'll assume that oxygen and hydrogen threads are created and started correctly and in the correct proportions, so the code that actually does that will not be shown. And I've also, in the upcoming code example, already converted the reusable two-phase barrier into C code. We talked about it as a pseudocode implementation, but I have provided the C equivalent of that. It's straightforward to convert, so it wouldn't be sensible for me to make that some sort of exercise. But we'll have queues for oxygen and hydrogen, and they both start as locked. That is to say, they have initial values of 0. Okay, so we're going to need a whole bunch of things. We'll have a count of the number of oxygen that is presently waiting. We have a count of hydrogen. We have a barrier mutex. We have a turnstile semaphore. We have a count for the barrier, which when we were talking about, say, n threads arriving, we had count, and that's the value that we're looking at here. And barrier n tells us the maximum number that we are waiting for. We have bond. And this is the semaphore that says only one thread can, or only one group can be bonding at a time. We have the queues for oxygen and hydrogen as well. Okay, and this is the C code version of the reusable barrier code that I had mentioned. To enter the barrier, lock the mutex, increment the count. If we've reached n, post on the turnstile, unlock the mutex, and then wait and post on the turnstile. And we are exiting from the barrier. Then we will lock the mutex, decrement the count. If barrier count is 0, wait, lock the turnstile behind us, and then we will unlock the barrier mutex as well. Okay, so what does the behavior look like for an oxygen thread? So the oxygen thread will attempt to acquire the bond semaphore and increment the count of oxygen. If hydrogen is at least 2, then post on the hydrogen queue twice, thus unblocking 2 hydrogen threads. Decrement hydrogen by 2. And then post on the oxygen queue, which will either push ahead whatever oxygen is ahead of us in line, or ourselves later when we get there, depending on the current value of the oxygen queue. Decrement the count of oxygen. If hydrogen is not at least 2, then just post on bond. We're just going to wait. So we'll post on bond and we'll get to the semi-weight oxygen queue and we'll get blocked there because we're not ready to proceed. There's not enough hydrogen right now. Once that's done, when we wake up, when we advance from the queue, we can go to bond, and then we have barrier enter and barrier exit immediately after one another. Finally, post on bond, and then this thread is done and can leave. So, the most obvious question probably is, why is barrier enter followed immediately by barrier exit? The idea behind that is that actually the oxygen queue and hydrogen queues will control access to bond at the beginning. The barrier enter and barrier exit just make sure that all 3 threads are ready before anyone is allowed to leave. So all that's required is they meet up. They don't have to do anything once they've met up. All we have to do is know that they have finished bond, and then they are allowed to exit. There's no requirement that they have to all meet up before calling bond. If that's how bond were implemented, then you would have to do that, but we would also need to make them wait after bond before anybody is allowed to leave. So it gets to be a little bit complicated, and it's perhaps a little surprising that enter and exit are followed immediately, because really all we need is for them to meet up after bond has happened. So okay, yeah, the oxygen thread isn't a super complicated one. Wait for bond, increase oxygen. If there's hydrogen, tell it to go. If not, well, that's okay. We know it's not going to be our turn, so we'll wait at the queue. And when we are awoken from the queue, then we can bond. We can then wait for the other threads to finish, and we can post on bond. And hydrogen looks like this. Again, wait on the bond semaphore, increment hydrogen. If hydrogen is at least 2 and oxygen is at least 1, then we will post on hydrogen twice, decrement hydrogen by 2, and post on oxygen once, decrement oxygen. So tell all 3 queues to let a molecule proceed, or tell both queues, but tell the hydrogen queue twice, to let an oxygen proceed and a pair of hydrogens proceed. Decrement oxygen count, otherwise post on bond, wait on the hydrogen queue. When it's our turn, we'll bond, and then we'll have our meetup with enter and exit, and that's it for a hydrogen thread. So, okay, there's a couple obvious differences between the hydrogen and the oxygen thread. One of them is that the oxygen thread just checks if hydrogen is at least 2. That's because, of course, if we are an oxygen molecule, we know oxygen is at least 1 because we exist, and therefore all we care about is whether there is hydrogen. If, however, you are a hydrogen, it's not enough to know that you exist. You also have to have a friend, or a buddy, or a partner, and an oxygen as well. In both cases, post on the hydrogen queue and decrement it by 2, and then post on the oxygen queue once and decrement the count by 1. If there isn't a package ready to go, then we just post on bond, sort of giving up our turn, and we get in line. So, yeah, again, the thread that calls post on the queue may or may not proceed, depending on whether there are items ahead in line. Okay, and as before with the fighters and the transports, it is a little strange that hydrogen threads don't post on bond. Not every time, anyway. They post on bond if they're unsuccessful, but if they are successful, they don't post on bond here after the barrier enter and exit, but oxygen threads do unconditionally. If you remember the explanation from before, you will know that actually this should not be a problem at all. Why? Because basically the hydrogen threads have given away this unpleasant task to the oxygen thread. So oxygen threads post on it unconditionally, and when a thread arrives, post will be performed if the bonding cannot occur. And when a bond can occur, all that matters is one of the threads does the post on bond. Doesn't matter which one. So at this point, the chemical composition of water says there's one oxygen and there's two hydrogen, and it's therefore simple to make it oxygen's job because it only has to happen once. If you put it in hydrogen, then we have to have some way of figuring out which of the two hydrogen is going to post on bond, and why should you add that extra complexity? The thread that's in the best position to do this is oxygen because it requires the least amount of coordination, so why not let it? You had one job. Okay, so we've covered a number of different concurrency problems. We started with the classical ones, the three biggest ones. We've, in this topic, covered a couple of additional ones, three really if you don't count the rebels escaping, and chemistry as being two separate problems. Four if you count them as two separate problems, and they are all a little bit more advanced than the first three, and accordingly we expect to see them a little less commonly in real life, but you never know. The design of your system could remind you of one of these. Or it could resemble nothing that we've seen before, because by no means is this set of problems that we've examined a complete listing of all of the concurrency problems that you might encounter. It is not at all comprehensive. There are lots more problems in the little book of semaphores if you were interested in reading about some of them. Many of them are quite obscure. Many of them have a particular use case, but they're not as popular. And yeah, ultimately, we could spend lots and lots of time on that if we had nothing else to do. And we could, drill down into every individual problem and every variation of every problem. But we've done well with the time that we have. And from here on out, we will just leave those other ones as something you can read about if you like, if you're interested, if you're curious. But for now, we will move on to our next topic. And our next topic is still in the subject of concurrency. We're going to learn a couple of more tools, in particular condition variables, monitors, and atomic types. Which are some more advanced tools, more advanced than just your typical semaphore and mutex type stuff, which will hopefully be useful to you. So that's it for now. See you in the next video.